So I would like to introduce our next speaker, Professor Uludag from Galatasaray University. Is it? Yeah, from Turkey. So, he will deliver lectures on PSL2Z. So please continue.
Okay. Thank you very much for the introduction. Well, this is the final lecture of today, and my other lectures will also be the final lectures. So I consider this as an opportunity to relax and because I'm going to talk about something really simple. At least in my first talks, I'm going to give a very basic, down-to-earth definition of the modular group and so on. And I hope that everybody in the audience will be able to follow and understand. And the following lectures will become gradually more and more involved. But it will remain understandable for everybody, I hope. So my talk is about the modular group, PSL2Z. And I'm sure that everybody encountered this group in his mathematical life at some step. And because I have also encountered it in several different contexts, once I have told one of my friends that I wanted to write a book about it. He told me that one rather needs an encyclopedia because it is so common. I mean, it can just pop up in some apparently independent or unrelated context, even to group theory, that it has something which has many avatars, as one may say here in India. So my aim here is, of course, not to talk about all those manifestations of the modular group, which is impossible to do in one lecture series or even in a school. But I'm going to rather concentrate on the structure of the modular group itself. How can we understand it in a as concrete way as possible? And so I'm going to start with introduction and basic definitions. Then I'm going to talk about the historical definition, which is related to antipyresis. Antipyresis procedure of Euclid, which is a very fancy name, but it will turn out to be something that we all know very well, and continued fractions. In my third lecture, so I mean, I'm not sure if this will be shorter than one lecture, so I'm going to be skipping to the second lecture in my first talk, perhaps. Then I'm going to talk about some miscellaneous facts. For example, the fairy tree. And the boundary. And at this point, we make contact with Olga's lectures. I mean, what I'm going to talk about is the starting point of the Bas-Serre theory, in fact, the modular group. And in my fourth lecture, my aim is to expose the structure of the category of subgroups of the modular group. Together with the action of, so this category, well, category is just, in this context, is just a fancy name for a directed set, in fact. So all subgroups of a group forms a directed set under inclusion. So which is a categorical structure also. And this category I denote sub PSL to Z. And together with a quite concrete description of this category, we can simultaneously describe the action of the group itself on this category by conjugation. So we are going to be exposing this structure, and it will turn out to be quite simple and understandable. In my fifth lecture, if I have time, if time permits, I'm going to relate this structure to the mapping class groups. So the last talk is going to be a research level talk, if I get there. Okay, so we can start. So I'm going to give, so usually most of you, I'm sure that have encountered the modular group in the context of hyperbolic geometry, where it arises as the group of, discrete group of isometries of the upper half plane. So for most of you, PSL to Z is just a subgroup of PSL to R. However, this group is more fundamental, much more fundamental and important than this one, I think, because the real line itself arises as the boundary of this group. So it needs a separate and independent definition from this context. Which we all know very well, in fact. So let me give that definition. So let phi be an element of the automorphism group of Z square, where here we consider Z square as an abelian group. Then phi is determined by its values, phi 1, 0 equals PR. If I know these values, QS, then I can determine phi MN as M times phi M times phi 1, 0 plus N times phi 0, 1, which equals PM plus QN, RM plus SN. And which we can write in matrix form as phi MN equals PQRS times MN. And since automorphisms, I mean composition of linear maps, corresponds to the matrix product, we see that the automorphism group of Z square is isomorphic to the group GL2Z, which is the group of integral matrices such that P, Q, R, S are all integers, and PS minus QR equals 1. Of course, we know that if P, Q, R, and S are integers, then phi is invertible if and only if as a map from z squared to z squared, we know that if it's an automorphism, it's invertible. But if phi is given in this form, then this is invertible. If and only if the determinant PQRS is 1, because in this case, we have an explicit inverse, because phi inverse mn in this case is given by 1 over ps minus qr. Excuse me, determinant is plus or minus 1. S minus q minus r p times mn. So this group is sometimes called the homogeneous modular group. We also have the determinant map from GL to Z to plus minus 1, which is a homomorphism, and with kernel SL2Z, which is a set of integral matrices P, Q, R, S, such that P, Q, R, S are all integers, and PS minus QR is plus 1. Here I see that I also forgot to write plus minus 1, which is also sometimes called the modular group. I mean, we encounter in the literature quite often that both these groups are called the modular group, but my modular group is this one because its structure is somewhat simpler than the group SL2Z. So this is a subgroup. This is a subgroup of index 2 inside GL2Z. So also there is some terminology which I would like to explain. This is called the group of unimodular. Instead of writing in this way, sometimes it is written as it is described as a group of unimodular integral matrices, group of unimodular integral inversible matrices. So integral means that entries are all integral, and unimodular means that the determinant is 1 here. Now we introduce an equivalence relation. On z square via, which is just the projectivity, in fact, n is equivalent to n prime, if and only if L times mn equals k times n prime for some k, L integer but non-zero. And we denote the equivalence class by m. The set of equivalence classes is denoted by P as P1Z, which is called the projective line over integers, and which is just the set of Mn such that the couple Mn belongs to Z square. It's a small exercise that the group automorphisms of z square are compatible with this equivalence relation. This is an exercise, and exercise includes making a sense out of the term compatibility as well. And because of this compatibility, every automorphism phi induces a bijection of P1 of the set P1Z, which we can write as F phi sending the equivalence class P1Z to M PM plus Qn Rm plus Sn in P1Z. And we have one more thing. There's a one-to-one correspondence. There's a bijection between. There is a bijection between this set, as we all know very well, and between Q union infinity, which sends this equivalence class to M over N. Here, F phi infinity is by definition P over R, and F phi minus S over R is infinity by definition, assuming that phi is given in this form. So if we do this identification, if you identify pi 1 z with Q in this way, then this map becomes a map from Q to Q. I mean Q closure to Q union infinity to Q union infinity. And we can express this map as sending M over N in Q union infinity to PM plus Qn plus over Rm plus Sn, which is in Q union infinity. And this is an example. This is called a linear fractional transformation or map, which is a much more general term, which applies when P, Q, R, and S are complex numbers as well. However, here we must add the adjectives unimodular integral linear fractional map. So instead of denoting this map as in this form, we just will denote F phi like PM over Qn over Rm plus Sn for simplicity. So the set of linear fractional transformations induced by elements of P of GL2 Z will be denoted as the projective group PGL2Z. And which is a group under functional composition, as you may verify. Which is a group under functional composition. In fact, we have shown that this is a group under functional composition. However, it's a pleasant exercise to check this directly, meaning that if you compose two fractional maps of this form, you obtain another fractional map of this form. Okay, now the map GL2 Z to PL2 Z is a homomorphism which you might also verify directly, which is a mere repetition of the previous exercise. And this means that the group PGL to Z is nothing but the group GL to Z over identity, because this automorphism has the kernel with kernel plus minus identity. So, and finally, we know that this kernel is included in the subgroup SL2Z that I just described, is normal. And the quotient SL2Z over plus minus identity is the group PSL2Z, which is our main hero, which is the modular group. So I started from the automorphism group of the group Z square. I projectivized it, and I have chosen a subgroup of elements of determinant 1 to define the modular group. This is our main hero. I'm going to sum up everything in a big diagram, but before that, I have to give one more motion, which is PSL2N. This is the group of monoid of PQRS, such that PQRS are in Z positive integers, non-negative integers, and determinant is PS minus QR is 1. This is a monoid. This is a monoid, and it depends on the choice of a basis for Z square. That is to say, the definition of SR2Z, etc., was independent of the choice of a basis for Z square from the very start. However, since here I talk about positivity of the entries, by changing the basis, I may end up with a different submonoid of the group SL2Z. So we may define the groups P, G, L to N and GLN, GL to N and SL to N in a similar fashion. And it is an exercise to show that this is in fact isomorphic to this one, and this is isomorphic to this one. Well, one more thing, which sometimes causes confusion. So we have elements of this group which are unimodular integral linear fractional transformations, which are like this. Whereas the elements of the group GL2Z are matrices. However, sometimes we use the same notation to denote the both elements. Elements of the both group are denoted elements of PSL2 or PGL2 Z are often denoted by the corresponding matrices, by matrices. So instead of writing Px over Q, Px plus Q over Rx plus N, we write just P, Q, R, S. However, if we denote it like this, this linear fractional transformation like this, then this and the negative of this element, minus P, minus Q, minus R, minus S, denotes the same linear fractional transformation. So, and one more thing, we have described the determinant. I mean, we all know about the determinant map, which goes from GL to Z to the set plus minus 1. This map descends to the quotient PSL PGL to Z, PGL to Z, again as a map plus minus 1. As a homomorphism, which is really easy to check. And with this one, I can now sum up all the objects that I defined until now in a diagram. So we have the exact sequence SL2 Z included in GL2Z, which is isomorphic to the automorphism group of Z square, and SL2Z is the kernel of this one under the determinant map. And from SL to Z, I have the inclusion map. Excuse me, I have the quotient map to PSL, PSL to PSL to Z, and which is a subgroup of PGL to Z, and in fact it is the kernel. Since this map descends, the determinant map descends to this group. Here I have this determinant map, and these are also exact sequences. No, the kernel here is the subgroup generated by So my main hero lies here, which is the modular group, PSL2Z. And in fact, there is really no big difference between these four groups, because this is a subgroup of index 2 inside here, and this is a subgroup of index 2 inside here, so that this is a subgroup of index 4 here. And well, that is why, since these are quite big infinite groups, we can say that there's not a big difference between them, and in fact, we may call any of them the modular group, in fact. However, as I said, this has the simplest structure among these four groups. This is why I'm going to concentrate on this group, and if you understand the structure of this one, then we can easily understand the structure of the others. So, now what about the elements of the modular group? I have defined a group, in fact, four groups. However, I didn't give you a single element inside these four groups, so they can be all trivial groups. However, the elements of this group is related to the following fact, which is called the Bezout lemma. Integers P, Q in Z are coprime if and only if there exists R, S, again integral, such that PQ, no, PR minus QS is 1. It could be minus 1 also, but let us pick just 1. No, I said if and only if. No, okay, if and only if, this is right. So that we can easily give some elements of the modular group. So if I put, first of all, if I put some number here, I want to write down an element of the modular group. This means that, first of all, if I put some number here, 3, then here I cannot put a number divisible by 3, or which is not coprime to 3, because then the determinant will be divisible by that number. So I have to put something coprime to it, for example, 7. Now, I'm sure that somebody can find two integers such that the determinant is just 1. Can somebody do that for me? What? 2, 5. 2, 5. So we see that from this group, all these groups are many elements. So among these elements, there are some which are more simpler than the others, and I'm going to give them some names because I'm going to use them often in what follows. So after the unit element, of course, the unit element is the simplest element, but then what comes after, for me, the simplest element is 0, 1, 1, 0, which written as a linear fractional transformation. So I'm inside PGL2 Z now, and I claim that this is the simplest element after the identity element of this group. So in matrix form, this is like this, and in the written as a linear fractional transformation, this is just 1 over x, and I'm going to name this the element u. However, since the determinant is -1, this is not an element of the modular group, right? And what is the simplest element of the modular group? For me, it is the element 0, -1, 1, 0. Now the determinant is +1, and if I write it as a linear fractional transformation, then this is -1 over x, and I'm going to call this transformation S. And finally, the second simplest element of the modular group is the element 1, -1, 1, 0. Again, this is in PSL2Z. This is also in PSL2Z. And written as a linear fractional transformation, this is 1 minus 1 over x. And I'm going to call this transformation L. So we are going to see that, first of all, these three simplest transformations generate the full group PGL2Z. Secondly, these two elements, these two simplest elements, S and L, generate the modular group PSL2Z. And this element is, it is easy to see, this element is of order 1, S square is identity. And this element is also somewhat surprising. I mean, it is, well, it is not somewhat surprising. It is really surprising for me. Each time I verify this, I am amazed. This element is of order 3. So now, at this point, I have a request from the students. Please check this. Please check that this linear fractional transformation is indeed of order 3. Can you do that? Right now. So as I said, at this point we make contact with Olga's lectures, as we are going to show that this group is isomorphic to the free product of the subgroups generated by S, Ln, which can be also written as the group as Z2, Z over 2Z, star Z over 3Z. So did you succeed? Are you surprised? Or this is just a banal fact? I don't have an explanation. It's just a fact of life for me. There's no explanation for this. Now, if you try to check that this is of order 3, this is not of order 3. If you take the third power of this element, it's going to be the minus identity. So if you consider this as a projective matrix, then it is indeed of order 3. And, well, that's it. So, okay, so once we introduce a mathematical object, we are immediately tempted to, of course, first to understand its structure. And if it turns out to be rich, then we want to generalize it. And in this sense, PSL2Z also admits many generalizations. And one immediate generalization is, well, I have 2 popping up everywhere. I started up with the group Z square. So instead of Z square, just consider Z to the power n, which gives me the group GLN instead of GL2, GLN Z. And I can also immediately define the group SLN Z. And similarly, I can define the group PGLN Z and PSLN Z. So you may think that these are the generalizations of the modular group. However, As I mentioned at the start of my introduction, this group appears in many other contexts. For example, it appears as the simplest mapping class group, the simplest non-trivial mapping class group. And in that sense, every mapping class group is a generalization of the modular group. So in another context, you come up with other types of generalizations. And in some contexts, you may obtain some generalizations in a completely different sense. For example, you may, for example, generalize even more and define the group GLA, where A is a commutative ring with identity. In this case, one must be careful because this group refers to the group of ring isomorphisms of A, not the group of all abelian group automorphisms of A. For example, if I write GLR, this is quite simple because this is considered as an R commutative ring with identity. Then it hasn't so many automorphisms, but if you consider the automorphism group of the full abelian group, this is much bigger than this one. So here we consider the group of abelian, not abelian group of automorphisms, but ring automorphisms. So this construction respects ring homomorphisms. That is to say, if I have a ring homomorphism from A to B, then I have a group homomorphism from GL to A to GL to B. So in this context, so we have another generalization. So GL to 2 becomes a functor from commutative rings with identity to groups. So, which can be viewed as a completely other kind of generalization. However, since it admits many different generalizations, this should not lead us to think that the modular group PSL to Z is the simplest and the most miserable element among all these family of generalizations. No, it is not, because its structure is at the same time more simple and more sophisticated than many of those generalizations. And in a sense, for example, when we will, if I have time, talk about the mapping class groups, we are going to see that in some sense it gives birth, it is somehow in a sense hidden inside the mapping class group, or the category of subgroups of the mapping class group. So they are born out of it. They are not some simple-minded generalizations of the mapping class group. Okay, how much time do I have left? 15 minutes, okay. So I have time to talk about the antiphyresis. So are there any questions so far? I hope that everybody have been able to follow everything. Okay. So this was a sort of modern introduction to the mapping to the modular group. We gave a definition in really modern terms, but this doesn't explain why this group is so important and why it appears in so many contexts in mathematics. In order to understand that, we must go back to the antiquity. So one of the problems that Euclid considers in his book is the process of antiphyresis. And it must be going back to at least 1,000 years before Euclid. I don't know if it's it's an exaggeration, but this is something really simple. So I would be surprised if somebody else didn't discover this before. The problem is the following. So this is a fancy name, but if Atanas will correct me, this means that something like repeated subtraction. Am I right, Atanas? So we have two sticks, one like this and the other like this. Let's call this the stick A. Let's call this stick the stick B. I want to make this a little shorter. And I want to compare their lengths. I want to compare the lengths of these two sticks. So what can we say? The most roughest thing that we can say about this is that A is greater than B, right? But can we refine this answer a little bit more? For example, one thing we can do is to take a meter, measure both lengths. Let's say that this is, I don't know, 35 centimeters. This is 21 centimeters. And if I take the ratio, 35 over 21, this would give me an idea about their comparison, right? This is exactly this times bigger than this stick. This stick, the stick B is exactly this times bigger than the stick A is bigger than the stick B. However, there are some problems about this idea because, first of all, to do this I need a meter, which was something decided upon after the French Revolution. So it is just an idea which is 300 years old. However, the problem is thousands of years old. And inside the problem, there is no centimeter. So I add something, some notion which do not belong to the problem to solve the problem. So this is something bizarre. Can anybody suggest another way of doing this? More refined way of comparing the lengths of A and B without measuring them by a meter. Yeah, we can take 2 copies of B. We can take 2 copies, and in this case, even perhaps 3 copies. And I can say that A is greater than 3 times B and less than 4 times B. So this is a better approximation to our problem, a more refined answer to our question. But can we go further? What if I want to know more about this comparison? So the idea is, well, I'm sure you all know very well. I just call this quantity. This, I write A equals 3B plus C. And then I compare B, the length B with C. So I write B equals 2 times C plus D. And I can go on like this. And Euclid, in his book, in a really, how to say, barbaric way of explaining what he did, but in his book he explains, proves in a very elaborate way that if A and B are commensurable, that is, if they are multiples of some same segment, a little segment of the same size, if they are multiples of one little segment, then this process ends. And this process is called the antiphyresis process. So this process stops at some point and gives us, in modern terms, the ratio of the numbers A and B as follows. I don't know, perhaps just Perhaps 3c. For me, 2c. I mean, if putting 3 would be dangerous because people would think that you have 3's all along, which appears in the congruence modular groups, by the way. Anyway, something like this. So this procedure will go on and end at some point. So, but my initial question was to know about the comparison of their sizes. So comparison of the size is the ratio for us. So I can write down, again, making a big lapse and coming to the modern times, I can write A over B as 3 times B over A plus C over A. Now, right? Am I right? No. This should be, I divided by, okay, this is just 3 plus 3 over B. Now, I want to know C over B. What's C over B? I don't know C over B, but I can, from here, I can compute B over C. I can divide this by C, and I can write B over C equals 2 times D over C. And I can go on like this. And if I collect everything in one place, I obtain A over B, which equals 3 plus 1 over 2 plus 1 over, etc. plus, so this will end at some step. Let me call the last number M. So this, I think, satisfactorily, in a satisfactory manner, solves our initial problem of comparing these two magnitudes. So, of course, given 2 sticks, they are not automatically commensurable. We don't know a priori if they are commensurable, but we can apply this idea to some other contexts. For example, if I have 2 piles of grain, okay, then these 2 piles are 2 magnitudes which are commensurable because they are multiples of the same unit, which is just 1 grain. So if we apply this procedure to grains, to piles of grains, then we know that this procedure will stop and will give us a precise idea about the comparison of their sizes. Now, I'm going to mix history and modern times a little bit, and I want to write this as I want to introduce 2 transformations, T, which sends X to X minus 1, and U sending X to 1 over X. Then I can write down this procedure in some general way as follows. So if I call this N0, this N1, and the final one Nk, then I can encode this procedure as T dot to the power Nk times U times T dot to the power Nk minus 1 dot U, etc. dot U T dot to the power N0, and we have our initial ratio. Okay, so we applied these procedures to our initial ratio, and we ended up with the number 0. I just wrote down this procedure in some modern operator theory language. So we can reverse the procedure and write this as T to the power N0 times U times T to the power N1 times U times T to the power Nk applied to 0 gives our ratio. Here, t is just t minus 1, which is which sends x to x plus 1. And u is sending x to 1 over x. So if I encode this as a continuous fraction, as before, we are going to obtain, we can write this as a continuous fraction as well, n0 plus 1 over n1 plus 1 over nk plus 0 equals our ratio rho. Here, please notice that t is the transformation sending x to x plus 1. And if I'm not mistaken, so s was, what was s? S was minus 1 over x, and L was 1 minus 1 over x. So if I combine these two operators, if I look at ls, this will going to give me t. So ls equals t. So that this belongs to PSL2 z, which is perhaps the simplest element after S and L in this group, by the way. So this group is in the group PSL2Z. However, U is not inside PSL2Z. We can say that, in a sense, the group or the monoid, because all numbers here are n0, n1, and so on, are positive integers, we can say that the group GL2N, the monoid GL2N encodes the possible antiphyresis processes. So if we want to compare two magnitudes, this group should pop up in a natural manner. So it is not surprising, isn't it, that if you do mathematics, because mathematics is very often about comparing magnitudes, so if you do mathematics, at some point we discover this group GL2 or the monoid GL2N somewhere. However, this correspondence or this explanation for me is not perfect. And in my lecture, I'm going to give a perfect explanation or some perfect correspondence, this time between the group, not the monoid, but the group PSL2Z, I mean the full modular group, and another kind of comparison process, which is really similar to this one. And I'm also going to show that this group has a boundary. This group has a boundary, which this time encodes all possible infinite comparison processes, infinite antiphyresis processes, in a very natural way. So I would like to stop at this point because I don't want to, I'm explaining this correspondence would be a very nice point to start my next lecture. Thank you very much for your patience. There's a question?